we often make assumptions about the physics of the inverse problem without even realizing it. These assumptions are often built into our software and include that gridded magnetic data is an accurate reflection of the in situ magnetization. Another assumption is that remanent magnetization is not present or negligible. In this study, we focus on whether magnetic modelling techniques can be used to inform our understanding of the structure of the Amadeus Basin, utilising the amazing stratiform magnetic anomalies present here, which preserve complex fold patterns throughout much of the basin. The Amadeus Basin is very large, and we can't examine all of it, but we will focus on the northeast of the basin, which is easily accessible from Alice Springs. We'll focus on three areas: the Waterhouse Range antiform, the Ross River synform, and the Finke River area near Glen Helen. The Waterhouse antiform preserves stratiform magnetic anomalies, as you can see here. They're quite subtle in total magnetic field data, as is the case throughout most of the basin, but using various filters, such as a bandpass filter seen here, or indeed using vertical derivative or an analytic signal filter, we can highlight them much better. Okay, because we're not allowed to do petrophysical sampling in these areas, our methodology was to measure the structure of the beds in order to constrain the petrophysical properties. And that's generally the opposite of the way we use petrophysics. We only took measurements where we were sure that we were seeing bedding, and we took 3 to 5 measurements at each site to ensure uniformity. The structural data indicate that the folding is very simple, as you can see here. This data was integrated with the geological mapping in the area, which was ground truthed along this transect by the NTGS. So both these data sets together constrain our magnetic modelling. Magnetic modelling showed here, it shows conclusively that some units, such as the Marini Sandstone and the Hermannsburg Sandstone, are dominated by downward inclined remanents. They correspond to subtle lows within a broad regional anomaly, and that broad regional anomaly is related to much deeper bodies. The disparity between the modelled remanence directions and the measured data, as shown in the stereo net, suggests that folding took place after the remanence was acquired. So now we're going to head to the northeast to Ross River to explore this concept further. At Ross River, we focused on the Arumbera Shale, which forms a prominent ridge, as you can see here. Unit crops out on each limb of a relatively simple synform, as you can see here. And the upper hemisphere stereo net on the right gives us a good feel for the morphology of the fold. So although it looks a bit complex in map view, it's actually quite a simple fold that's just been faulted. The structurally constrained modelling shows that on the northern limb, the unit is associated with a positive magnetic anomaly, as you can see there, whereas on the southern limb, the unit is associated with a negative magnetic anomaly. And this clearly shows that remanent magnetisation is present. It's important to note that in this unit, the magnetisation is held in a sort of highly oxidised hematite-rich shale unit. A basic fold test was applied to the magnetisation directions from both the northern and southern limbs, and you can see the orientation of each limb on a north-south cross-section here with the modelled magnetisation shown. We simply rotate the northern limb 35 degrees north and the southern limb 25 degrees south, such that both layers are horizontal and reflect the pre-folding surface. This test shows quite convincingly that remanent magnetisation was acquired pre-folding, probably during lithification. We'll now go to the Finke River area near Glen Helen, and we'll look at two areas as shown on the map here. In the first area, South Glen Helen, there's a linear anomaly associated with the Brewer conglomerate. The anomaly is a simple positive anomaly, and the modelling suggests that it's predominantly due to induced magnetisation. And you can see that unit there, it's coincident with a grey band within generally redder bands in the Google Earth imagery. And this suggests that the magnetised layers are in fact reduced magnetite-rich horizons. so quite different to the previous example. In the other area, north of Glen Helen, there's a series of conformable units leading north into a major unconformity surface. And beneath that unconformity, or north of that unconformity, there's complexly deformed evaporitic and carbonate sequences. The total magnetic field data, as you can see in that middle image, is quite subtle. But the stratiform anomalies are revealed using bandpass filter or a first or second derivative filter. The second derivative filter appears to provide the best detail, but even this is flawed, as we'll see in the next slides. If we try to model these anomalies using line data, we find that the line data is not actually very consistent from line to line. So in that little circle there, you'll see that the morphology of the anomaly in that particular area is quite different from line to line. And we're looking at the first vertical derivative on the top there. There's two main reasons for this. The first is that the anomalies are so thin and so close together that they overlap. That is, the magnetic fields add to each other to form poly-source anomalies. Using the line data, we need a lot of sources to explain the anomalies present, many more sources than are indicated from filtering of the gridded data. So I just want to focus on these three on the right here to explain what's going on. So you can see in this synthetic model that the three bodies form one anomaly in the data. However, when we separate them, they form three separate anomalies. So really, what we're seeing everywhere is that single anomalies are due to multiple sources. And unfortunately, this kind of scenario is the rule rather than the exception in the Amadeus Basin. And consequently, we can't really use the magnetic field data alone to map structure, because the anomalies are just not well separated enough. And it's because the sensor is too far away from the source. The second issue we have is that due to the high relief over the Glen Helen quartzite, the survey plane is at very different altitude, flying north versus south. So every effort would usually be made to adjust for this in the processing, but it's just not possible for short wavelength overlapping anomalies such as we see here. The overlapping anomalies coupled with the inconsistent drape are really a double whammy for modelling in this case. And we really need to do a ground survey to get a much more accurate reflection of the in situ magnetisation. So, some conclusions. Magnetic anomalies can be due to predominantly induced magnetisation, which is commonly associated with intermediate redox and magnetite-rich sources, generally coarse magnetite. We've also shown they can be predominantly due to remnant magnetisation, which in the Amadeus Basin is generally related to oxidised hematite-rich units, but in other places can be due to monoclinic pyrrhotite. But more importantly, the total magnetisation is by definition the vector sum of both. In most cases, remanence is equal to or stronger than the induced magnetisation. In the Amadeus Basin, remanence appears to be dominant in many cases, and it predates folding. So it's not the same from one limb to the other. So narrow adjacent magnetic sources cause overlapping or merged magnetic anomalies. These are very hard to separate using line data, but once we grid our data, it's impossible to resolve such details. Gridding magnetic data often leads to unwanted artifacts. These can be caused by differences in the flying height or the drape and corrections thereof. Together, the narrow overlapping sources and the inconsistent drape mean that the magnetic data often do not reflect the in situ magnetisation of the area effectively. We therefore cannot use the aeromagnetic data to map the structure of the basin. So why should you care? Well, we've shown that the common assumption that magnetisation is predominantly induced is not really valid. It's not based on any evidence, and in fact it flies in the face of all evidence, as I'll show shortly. And furthermore, the common assumption that gridded magnetic data reflects the in situ magnetisation is often a poor assumption too, especially for near surface tabular sources. And the biggest problem is that these two assumptions are the basis for most modern approaches to magnetic field interpretation. So I just want to leave you with this slide. This is a plot of remnant magnetisation versus susceptibility with the Q or the Königsberger ratio shown there. And it shows that rocks with negligible remnants are effectively non-magnetic, whereas most significantly magnetised rocks have significant remnants with Q ratios of sort of 0.2 or 0.5 or higher. So this means that our general assumption is in fact the opposite of correct. Most rocks do have significant remnants. I just want to leave you with this. It's a nice picture of a non-stratiform magnetic anomaly in the Amadeus Basin. Thank you very much.